To finish off this first section on complex numbers, we're going to look at the relationship between polynomials and complex numbers. We saw it with the quadratic, but it's also true for every polynomial. If all the coefficients are real, then your solutions or your roots will appear in conjugate pairs. And that's because every polynomial can be factorised down to a combination of quadratic and linear functions, and we know every quadratic can be solved with the formula, you get plus or minus the square root, so you get conjugates. Every polynomial of degree n, as I just said, can be factorised down to be this mixture of quadratic and linear factors when we're talking about the real field. Of course, if we go over the complex field, then they'll just all be linear factors, because now we can factorise every quadratic. What this means is, if the polynomial is of odd order, so a cubic for instance, it must have a real solution. Because if the imaginary ones are appearing in pairs, well, that's going to create an even number. You've got one left over, so there's got to be at least one. Let's start with this quadratic. I'm going to do it by completing the square. It's nice and quick, this one. I get x plus 1 squared plus 1, which becomes the difference of two squares, one being minus I squared, and we get x plus 1 plus I, x plus 1 minus I. It's factorised. It's over the complex field, not the real field, but it is now factorised. Solving this quartic, mind you, it's a quartic that does look like a quadratic. We get z squared minus 3, z squared plus 4. Now, I don't really need to further factorise this one because it's an equation. I could just go solve this, but I'm going to do it anyway just to illustrate the difference between factorising over the real field and factorising over the complex field. You see, over the real field, then the z squared minus 3 can factorise to be z plus root 3, z minus root 3. The z squared plus 4 we can't do. But if we were to then take it over the complex field, now you could factorise the z squared plus 4. It gives us our four solutions. As I say, because it's an equation, I didn't really need to do those last two lines, because I could have simply gone from the second line and said, well, z squared is equal to 3, or z squared is equal to negative 4, and go from there. Remember our factor theorem. We know that if x minus a is a factor of the polynomial, well, polynomial a is equal to 0. So that's a way of trying to locate solutions. And if it's not a monic, then if ax minus b is a factor, then what we would substitute in is b over a. I want to factorise this cubic. Now, it is a cubic, so I know there is a real solution. Now, that real solution could be factors of 5. That's nice because 5 is a prime number, so that just gives me 5 or 1. Oh, of course, you could have negative 1 or negative 5, but it's not monic, so you could also have those divided by 2. That now gives me 5 on 2, 1 on 2, and the negatives of those. Of course, the logical first thing to check, because you want something easy, what would be the logical first thing to substitute in? That's right, negative a half. Now, of course it's 1, but I've chosen negative a half. Oh, what do you know? It turns out to be 0. That one works. That was lucky, hey. So I now know that 2x plus 1 is a factor. I can do a polynomial division or just look at it using logic. The other factor, therefore, is x squared minus 2x plus 5, which then I will factorise down. Again, I'm doing it by completing the square. So it's x minus 1 squared plus 4. I get x minus 1 minus 2i, x minus 1 plus 2i. They've told us that this one has two rational zeros. Okay. In other words, if they're rational, they're not imaginary. Okay. We're talking about real solutions. Find these zeros and then factorise it completely, but over the complex field. So into linear factors. Okay. Two rational zeros. Nicely, the constant, again, we've got a prime number, that's 3, so that gives us 3 or 1. 4 being the coefficient of x to the 4, because it's got factors in itself. So we could have 3 over 4, we could have 3 over 2, we could have 1 over 4, we could have 1 over 2. We could have the negatives of all those. Again, the logical first thing to choose would be a half. No, of course it's not a half. But oh, what do you know? It turns out to be 0. So I now know 2x minus 1 is a factor. It's going to look something like that. 2x minus 1 times something. We know the leading term times the leading term gives us the leading term. Therefore, it starts with 2x cubed. I know the constant times the constant. It gives me the constant. So I know it's 3 there. Okay, how many x's do we have at this stage? We know we want 1x. At this stage I have 6x. How do I get from 6 to 1? I subtract 5, so the negative 1 must have been times 5x. Okay, we have that term now. Now maybe I'll go from the other end, the cubics. At this stage I've got 4x cubed. I want 8x cubed. Therefore, that one must be 5x squared to get the balance out. Oh, but it's still a cubic. But I do know this cubic, well, one, because it is a cubic, it must have a real solution, but also they told me there were 2 anyway, so I know there's another one. I look at this one, okay, 3's still there, got to go into 3, 2, logical pick, this time negative 3 on 2, yeah, that makes sense. That becomes 0, so I now know 2x plus 3 is a factor. So the first part of the question was find these zeros. I found the 2 rational zeros. It's a half and negative 3 on 2. I still need to complete our factorisation. At this stage I have 2 linear factors, therefore what I'm left with is a quadratic. Again, I could go leading term times leading term. You might find it easier to actually expand those 2 out when you're doing the working out the other one. Up to you how you do it. But essentially I'm saying, well, how many x have I got at this stage? I've left it like that. I could have gone 1 times 3 times 2x, so I've got 6x. But I could have also gone 1 times 2x times negative 1. That gives me minus 2x. What's missing? Well, I've got to get to 4x to the power of. So the missing term there is x. This is where the factorisation is interesting because we're so used to always having whole numbers. Well, this one doesn't have whole numbers. We've got x plus a half squared plus 3/4. If it was an equation, not an issue. I could multiply by the denominator and everything would be fine. But this is not an equation, it's a polynomial. So if I was to now multiply to get rid of that, it would no longer be 4x to the power of 4, it would be whatever I've multiplied by. So I can't do it with this one. I have to leave it like that. I suppose you could factorise out a quarter and have a quarter sitting out the front, and then that'd be okay, you'd have whole numbers in there. But anyway, that's a factorisation. Sure, we've got fractions, but so what? Fractions are numbers. Another quartic, we've been told it has a real root, but it's of multiplicity 2. Then we've got a double root, something to the power of 2. We know, this time we've got more choices. Factors of 45. So even though it was monic, when you go great, 45's got a lot of factors. 1, 3, 5, 9, 15 and 45, and of course it could be negatives of those. Okay, logical first one to pick. Oh, hang on, before I do that, it's a double root, so I also know it's a solution of the derivative. That sort of narrows it down, does it? Because I know then that 9's not going to be it, because 9 doesn't go into 30. We know it's got to go into 30. It narrows some down. This time I did choose the logical one, but it didn't work. Damn. So I know the double root's not 1. I'll try 3. That one did work. Not necessarily is that the double root, that's possibly the double root. It's a solution, but it has to be a solution to both. If I substitute it into the polynomial itself, yes, okay, it is a double root. It satisfies both of them. We now know z minus 3 squared is a factor. Let's find the other factor. Leading term times leading term. The leading term, remember this is squared, so we've actually got z squared here, would be z squared. Constant times the constant, but that's minus 3 squared, which is 9. Therefore I've got 5 there. The question then is, what is the missing term in the middle? Actually turns out there is no missing term. It's just z squared plus 5, the other factor. Well, again, I suppose, I'm just looking at the question, I didn't really need to factorise that because it is an equation to solve. I could have now gone straight from there. But anyway, I have factorised it. It would be z minus root 5i, z plus root 5i, but we get our solutions to the equation. Let's finish off with an HSC one. A couple of years ago, it was a nice one. You'll notice it's 16D, so it's right at the end of the paper. Find all the complex numbers, Z1, Z2 and Z3, that satisfy these 3 conditions simultaneously. So the modulus of all 3 are the same. If I add them up, I get 1. If I multiply them together, I also get 1. We simply have to find the complex numbers. First thing I'm going to say is, well, I know the modulus of Z1, Z2, Z3 must be 1. But if the modulus of Z1 equals the modulus of Z2 equals the modulus of Z3, then that's the same as saying Z3 cubed is equal to 1. Okay, I know the modulus of Z3. Now, I'm going to play around with this multiplication. Z1, Z2 would be equal 1 over Z3. And I know the reciprocal of a complex number is its conjugate over the modulus squared. So I now know that Z1, Z2 is actually the conjugate of Z3. I could have played with any of them. I could come up with the same result. Z1, Z3 must be the conjugate of Z2, and Z2, Z3 must be the conjugate of Z1. And you think, well, how is this helping me? Because now I can work out what this expression is. Z1, Z2 plus Z1, Z3 plus Z2, Z3 must be the conjugate of Z1 plus Z2 plus Z3, which you've told me is 1. So I know that is also 1. How is this helping me? Z1, Z2, Z3, that's what we're trying to find. It would be a solution to some cubic. It would be this cubic. Sum of the roots 1 at a time would be the coefficient of x squared, or negative, because you get minus b on a. Sum of the roots 2 at a time would be the coefficient of x. Sum of the roots 3 at a time would be the constant at the end, or again, the negative of it, because it goes negative, positive, negative. That's why I wanted to find each of those expressions. They told me the Z1 plus Z2 plus Z3. I just worked out the Z1, Z2 plus Z1, Z3 and so on, and they told me the Z1, Z2, Z3 as well, I think. There's the cubic. Remember, I'm looking for the solutions to this cubic. Okay. Factorise. X minus 1, x squared plus 1 equals 0. I have the 3 solutions. I now know what they are. So one of them is 1, one of them is I, the other one is minus I. Nice little question. Okay. Now, 1G, again, I've put in an exercise from Patel to look at as well.